Lovely conference. It's really a great pleasure to be here. Actually, my first time in Poland. And I must say, I'm, for those of you who know me, I'm not an operator theorist. But anyhow, Tatuamasi came to Ben-Gurion a few years ago, and he was a postdoc of Yair, and he came in with this very intriguing question. So here's Tatuamasi's question. Understand, say you have an action of a discrete group, you can talk about a topological space or alternatively probability preserving action. So there's kind of a topological dynamical version of this question, or an ergodic theory version. And you want to classify or understand the intermediate algebras of the following form. You look between the reduced C-star algebra of the group and the cross product. And the reason that it seems intriguing is it somehow subsumes much of dynamics, in the sense that one example is if you have a factor, given any factor. So let's talk about the topological dynamical setting. Sorry, I could have written this also in the measurable. I can talk here between L gamma and L infinity x mu, kind of a measurable cross product. And the point is that any factor of the dynamical system gives rise to one such intermediate algebra. Any factor, say from X, let's talk about the dynamical case, from X mu to Y nu, it's a gamma factor, gamma equivariant factor, which is, one of the main structure tools in dynamics. Gives rise to an intermediate algebra because here inside L infinity you get the L infinity of Y. So you can find gives rise to an intermediate algebra of the form L infinity Y nu. Cross product with gamma, and the question is, is this everything? Or if not, can you kind of try to build a structure of these kind of intermediate algebras, which is reminiscent to what happens in dynamics? Or can you understand the structure? There is very, very little that we can say so far, and us and other people, notably Suzuki, was interested in similar such questions. Luckily, I'm kind of familiar with somebody who is very into this kind of dynamics, so I brought him into this project, and so everything I'm going to say today is a joint work with Tatu Amasi and with Eli Glasner, so joint. And with Eli Glasner. Okay, following this question, let me first say a bit that we know to say. I'm going to try to distinguish between the case where gamma is C-star simple and the case that gamma is not C-star simple. So let me say a few words about the C-star simple, about the non-C-star simple case. The non-C-star simple case, in which case we found that sometimes at least, and this is the motivation for distinguishing between these two cases, there are non-dynamical factors that kind of originate in ideals of the C-star algebra. So we have two theorems here. Theorem 1, if gamma acting on X is probability measure preserving, so there is some mu, an invariant measure on X. I'm still talking here about the topological dynamical setting, like the C-star theoretic setting. And assume further that and gamma, just assume that X has at least 3 points and gamma is not C-star simple. Then there are many intermediate algebras let me just write curly A inside this square A, which do not come from dynamics. I mean, notably, you can kind of choose any ideal in the C-star algebra, and you can just choose any ideal in the C-star algebra, multiply it by the cross product from both sides, then add the reduced C-star algebra, and this will be an example. It requires some work. I mean, it seems kind of obvious. It's an algebra. It's not constructed in that fashion, but it's actually some work. I mean, to prove that these algebras are not of that form, that secretly there is no kind of factor that gives rise to this, it requires some work. We have to distinguish between the infinite conjugacy class case and the non-ICC case and so on. But this somehow indicates that there is more there than thing. Here is the second theorem that we proved that at least I found more fascinating. This is, we give a complete classification of all such algebras, but in a very, very simple, the most simple situation that you can come up with. So consider the system xt, which is just an irrational rotation on the circle. Let me not call it S1, but R mod Z, say. And in this case, we have kind of a complete classification. And again, the intriguing thing is somehow that the ideals in the reduced sister algebra, which is just the whole sister algebra in this case, play a very central role. So let me describe this complete classification. So here is the collection of all intermediate algebras. I can look here at an intermediate algebra A, and let me associate with it a sequence of ideals. I call them Cn, I can call them like Ca of n, if you like, which is consists of all the eta in phi star Rz such that e to the minus I n theta e to the minus I n x times eta fits inside the ideal, inside the algebra. If you look at it for a second, this is an ideal in the reduced sister algebra of Z, right? If I have two such etas.
Would you recall us what is reduced sister algebra of Z? Just algebra of functions on?
Yeah, it's just the functions on the circle.
On the circle.
Okay, but it's a kind of a different circle than this one. It's it plays a symmetric role in a way, but it's not this circle. It's a different circle.
Well, eta is a function, continuous function.
Yeah, eta is a continuous function if you want to think about it, but it's kind of important to distinguish between the two circles that are playing here. And I'm just pointing your attention to the fact that this is an ideal in C star Rz, namely it's just a function. I mean, this is just if you want, it's functions on S1. I'll call it S1 to distinguish it from X, because this is just the Pontryagin dual of Z. So this is an ideal, of course, because you see the intermediate algebra already contains the reduced sister algebra. So if I multiply it by any element in the sister algebra, it's still inside A, and of course it's close to addition. So associated with every algebra, I get a sequence of ideals inside this. I kind of, notationally, it's convenient to think about ideals here as closed subsets of the circle. So I just denote this by, let's denote by C bar n, thinking of it as a closed subset of the circle of S1. And once you do this, you get a kind of a list of combinatorial conditions. They are very simple combinatorial conditions that characterize and stand in one-to-one correspondence with intermediate algebras. So the theorem says that intermediate algebras stand in one-to-one correspondence with functions C from Z to closed subsets of S1 satisfying a few properties, namely C bar of minus n is tau to the n Cn, C bar of m plus n is contained in tau to the minus m C bar n union C bar m, and C bar of 0 is empty. The fact that C bar of 0 is empty corresponds to our assumption that we actually contain the whole reduced C-star algebra. So, in fact, in the 0 situation, if this doesn't exist, then we don't get. And then. Tau here, which is kind of intriguing, is the same irrational rotation that we started with, but on the other circle. Okay, it's kind of intriguing that the same irrational rotation that we started with on this space plays a role, but now on the dual circle. So this gives rise to a kind of an rather intricate combinatorial theory of which are the possible functions that that can arise, that satisfy these three combinatorial conditions. And it turns out that there is a rich theory behind this. There are many of these factors that do not come from dynamical factors. In particular, there is kind of a few different properties. So some of these.
Does the Diophantine nature of theta pops out?
Yeah, that's a very good question, and I'm not sure. I mean, I think this really deserves more structure somehow, more investigation. So we do look into it a bit. We have a few algebras that are very interesting. In particular, some of them have a center, others don't have a center. We get a very nice subfamily of algebras, which we call residual algebras. We call them residual because it's a bit confusing actually. We have here a sequence of sets that are closed subsets of the circle. So if these sets are meager, namely they are F sigma and have empty interior, this means actually that the algebra is large. And then you can kind of use Baire category. These are kind of especially nice family of intermediate algebras that are characterized by the fact that all of these closed subsets are meager, and this is, using kind of Baire category argument, you can show that this family is closed under intersections and that it has very nice properties. All of these are center free, and they have some nice properties. You could ask, what are the original, dynamical intermediate algebras that come actually from factors of the circle? The factors of the circle are just self-covers of the circle, of course. And these are characterized by periodic ideal functions here that basically just, periodically allow for Fourier coefficients, and whenever they do, they allow for everything. So the ones like this will just correspond to, the dynamical ones are just corresponding to C bar is equal to empty when P divides N, and the whole circle when P does not divide N, and P here is just the P correspond. This is the algebra corresponding to a P-fold cover of the circle. So these are some remarks on what we know about the non-C-star simple case. It's a very restricted piece of information, and it does seem like a difficult question. And this somehow brings us to try to vary this question and now ask, well, is this everything? Do all, so a revised question, do all intermediate algebras A in A come either from ideals or from factors? And this is very flimsy. I mean, we don't have any good evidence to support this. In particular, we don't even have any kind of good understanding in which way ideals give rise to intermediate algebras. You see that even in the very simple case of a irrational rotation, this becomes quite complicated. But it does lead us to consider the C-star simple case. So at least when there are no ideals, what can you say? So let me give two definitions, the kind of passing to the non-simple C-star, to the C-star simple case. Let me give a definition. We say that a system X gamma is reflecting if all intermediate algebras come from factors, from dynamics, and two, almost reflecting if E of curly A is contained in A, where here E, can you see if I'm writing down?
No, I think no.
So E here is just the kind of the canonical conditional expectation going from C of X cross product with gamma to C of X, namely one sending lambda gamma to 1 if gamma is 1 and 0 if gamma is not 1. Okay, so it's what's the connection between these two conditions? Why do we call them reflecting and almost reflecting? Well, reflecting is clear, right? I mean, we want the algebra somehow to reflect the dynamics. So this is the source of the word reflecting. So a few remarks. One, clearly reflecting implies almost reflecting, because, if an intermediate algebra is of the form C of Y cross product with gamma, and you hit this with the conditional expectation, you just get C of y, okay? I mean, you can think of this conditional expectation kind of schematically, you know, if you think of elements of this algebra schematically as sums f gamma, lambda gamma, then this conditional expectation just extracts the function that is in the coefficient, the constant coefficient, right? And then you will just extract this. So it's clear that reflecting really implies almost reflecting. In the von Neumann case, they are the same. Okay, let's look at the following situation. I have here L of gamma, and here I have some intermediate algebra M between the cross product and gamma. And now let's assume that we are weakly reflecting. So let's assume that that E of M is actually contained in M. Okay, now of course E of M need not be an algebra, but I can look at the algebra that it generates. Okay, it somehow sits inside L infinity. I can look at the algebra that it generates. Since this is an abelian algebra, this is going to be, this algebra that it generates is going to be L infinity of some factor. Okay, so let me write inside here, there is a kind of a good candidate sitting between M and here, which is where E of M, the algebra generated by this is just L infinity of y nu for some given factor. And now I would want to show that these are equal, but indeed, if you take any M here, then what you can do is try to extract its Fourier coefficients. Namely, I can look at the sum over all gamma of E of lambda gamma star M lambda gamma. And you see this fits in inside here, right? Because I assumed that, right, I contained the group algebra. I assumed that that I am closed undertaking the conditional expectation, and therefore this fits inside here. So for every M, sorry, for every M, I actually have this whole series here, which you can show converges to M, so you really get an equality here. Now, in the C-star case, this is not equivalent, but it is a theorem of Suzuki that if you have a nice enough approximation property of the group, so 3, a theorem of Suzuki, if gamma admits the property, approximation property AP, then this is equivalent also in the C-star setting. So this property AB, you can think of it some kind of a way that, you know, really doesn't give an equality, but kind of allows you to make a fair type approximation of the original element by some sums like this. Or right, it's always the story of Fourier coefficients. They don't really converge, and you have to.
What is AP?
It's some approximation property. Instead of saying what is AP,
Stronger than residual finance.
instead of saying what is AP, let me tell what groups satisfy this. Okay, so AP hyperbolic groups are AP. On the other hand, if you look at higher rank lattices, for example, they don't satisfy this approximation property. Higher rank lattices are not. Yeah, I mean, higher rank lattices have property T. I mean, there are some hyperbolic groups with property T, right? So property T is not the issue here. I mean, okay. So this is somehow the connection between these two, and we will be kind of, trying to establish this weak weak reflecting property, and in particular, if the group happens to be hyperbolic, then it will actually imply reflecting, but otherwise we don't know what to do. So Tatuamasi and Yongle already came with a very nice proof to this effect, and we are basically just copying their proof. So here is a theorem. Let gamma be C star simple, act faithfully on maybe I need let me say act freely and faithfully on a rooted tree, so basically looking at some kind of profinite actions. When I mean freely, I mean, of course, the boundary action is free. The action on the tree itself is never free. Then this action, the action of gamma on the boundary of the tree is weakly reflecting.
Weakly is the same as almost?
Almost.
Sorry?
Weakly is the same as almost?
Almost, yeah. So, and we kind of modify this proof, but so here is our proof now. We extend somehow the class of actions that we are talking about, but we reduce the generality of the groups that we talk about. Still, I want to talk about it because I think it gives a good view of the connection with C star simplicity, and this is the point that I am really trying to make. So let me give a few definitions. An action, you see, I'm all the time trying to talk about the topological dynamical side, but implying also the other. Here, let me give both of them because there is a little bit of a difference. So an action, X gamma, this is a topological dynamical system, is called rigid, uniformly rigid, Well, if the implied image in the homeomorphism of X is non-discrete, in the uniform convergence topology, this is where the uniform comes from. So in particular, you have a sequence of elements here in gamma that viewed as elements of X, they converge uniformly to the identity. And you can give the same in the ergodic theoretic setting is measurably rigid if, well, gamma inside ot x b mu is non-discrete. The Polish topology that I'm referring to here means that I have, I'll not write so low down, I want gamma n a converging to 0 for every measurable set. Okay, this is kind of the nice topology on the group of all measure preserving automorphism, the one that Francois was not mentioning. He was talking about the uniform, the strong topology, which makes the full groups Polish, but this is a good topology here. So this is a far-reaching generalization of this kind of situation. In particular, every equicontinuous action, and in particular a profinite action like this, is rigid, because, if you are acting equicontinuously, you're basically acting on a compact group by a group element, and you're bound to eventually, just by compactness, get arbitrarily close to the identity. So this is really this theorem of Tatwamasi and Jongle addresses profinite actions. You can try, and we were trying to generalize it to the equicontinuous case, but in fact, this is really much more general. So there is a recent theorem of Eli Glasner and Benji Weiss that actually says that any residually finite discrete group admits many rigid actions that are not equicontinuous. So this is, and I think somehow this is the right setting. So our theorem says that if gamma is hyperbolic, then every rigid action is reflecting. We need hyperbolicity here for two reasons. First of all, to ensure this property AP, to ensure this property AP that guarantees that we actually have not just almost reflection, but actual reflection. But in fact, if gamma is a convergence group, non-elementary,
terminology of Furstenberg-Tinker.
Exactly. Then every rigid action is almost reflecting. So let me tell you what is a convergence action, because this is actually what we're going to use. I think this is the essential point here. Yeah.
Is your theorem in the C-star category or
It's in both. This is in both. And in fact, if you, and it's an interesting question, because somehow I'm restricting myself to the C-star simple case, and it seems that it would be relevant to the topological dynamical setting, but really this theorem it works in both cases, and in the ergodic situation, in the von Neumann situation, you don't really have to assume hyperbolic. I mean, every convergence group will be actually reflecting, just because the equivalence there is. Yeah, so the theorem actually works in both situations. So let me just tell you what is a convergence group. It's you know, there's kind of an interplay between two schools, people who like hyperbolic groups because of the geometry. They are basically looking inside the action of the group on its Cayley graph and so on, the geometry of the Cayley graph. And the other school, I think maybe initiated by Bodic, is considering just the topological dynamics of the group action on its Gromov boundary. And then you can axiomatize it. A group is hyperbolic in the Gromov hyperbolic in the natural sense. And I think this is the theorem of Bodic, if and only if the action of the group on its boundary is proper and co-compact on triplets of distinct points. So
Which
this
boundary,
is
sorry.
sorry.
Which boundary?
The Gromov boundary. So a group gamma. This is the theorem of Bodic. Gamma is hyperbolic if and only if its action on its boundary is proper plus co-compact on triplets of points, of distinct points. You can imagine it on the tree, right? I mean, once you know where 3 points go to, you actually determine this is the type of situation that we want. And now, of course, these were, much generalized. Today, it's popular not to talk about hyperbolic groups, but maybe to talk about acylindrically hyperbolic groups, which is a much, much wider family of groups. It includes also OTFN and mapping class groups and so on. And from the topological dynamical point of view, you just do away with the co-compactness. So a group is convergent if its action on triplets of points on some topological space is proper. But more to the point, so let me give a different definition. The gamma acting on Z, and this is a different space now. This is it's kind of an auxiliary space to my discussion. It's not the rigid space that is given, is convergence if for every sequence of points, of group elements, there is a subsequence gamma and I and two attracting and repelling points, I kind of indicate their nature by their names, inside the space such that gamma ni converges to R uniformly on compact subsets of V minus the repelling point. So the picture is like this. I have here, after passing to a subsequence, I have an attracting point, a repelling point. Maybe they might be identical. And this subsequence basically it's kind of a north-south type dynamics, but it's the way you view a north-south type dynamics on the boundary, not on the space itself. It contracts everything outside of a small neighborhood here into a small neighborhood of this point. And it's a non-elementary convergence group if there is at least 3 points in the space. How much more time do I have?
12, 13 minutes.
Okay, so let me try to get to the point then. So somehow the idea of our proof, which I mean, really I think tries to make the connection with C-star simplicity, which really tries to make the connection with C-star simplicity, is really very much inspired by this beautiful note of Hagerup on the, there is a note, a new view of C-star simplicity, following all the works of Kalantar Kennedy and Ozawa Boyard, Kalantar Kennedy, and so forth. He's basically wrote this very short note posthumously, I think, which kind of connects the C-star simplicity, namely in its new version, an existence of a good free or topologically free gamma boundary, with the classical powers type averaging scheme that gives rise to C-star simplicity. And in particular, here is our so let me look here. I'm talking on the C-star setting. Let me take here AA, an intermediate algebra. I'm picking here an element A, and I would like to show that E of A is contained in A. So let me try to first approximate A. I can write it as some finite sum approximately of F gamma lambda gamma plus the constant part. And what we want to do is we want to try to extract this part, because this is, but we want to extract it just using algebra operations. That's the whole point, right? I want to show that E of A is also contained in A. I have to get rid of this disturbing part here, and for this we want to use a kind of a powers type contraction scheme. So if we can find some S1 up to Sm in the group such that 1 sum 1 over m lambda Si let me write lambda gamma, lambda SI star is less than epsilon for say a given epsilon. So I'm able, just using group operations to kind of diminish this whole initial part that we have. But at the same time, I want not to hurt this one too much. Okay, this is a function. This is a function on my space X. So if I'm hitting it with this operation, I want to say that 1 over m sum of, or let me just write it element-wise, lambda Si E of A, lambda Si star is epsilon close to E of A itself. And if you remember the definition of a cross product, this is just moving the argument here, right? I mean, that's the whole point of cross products, that conjugating by a group element really realizes the action of the group on the space. So this is this SI. So the point is that I want to use the C star simplicity machinery, but I want to use it not with general elements of the group, but with elements that actually manifest the rigidity. I want it to happen with elements that on the space X are converging uniformly, let's say, or in the measure theoretic sense to the identity. And therefore they don't change this part too much. So in order to achieve this, we kind of follow Hagerups strategy that basically shows that given a free action of, so Hagerup does the following: given a free gamma boundary, which now is known to be equivalent to C star simplicity. When I'm saying a gamma boundary, I want it to be a minimal and strongly proximal action. He kind of constructs a sequence of elements, lambda Si, which realize a contraction. And what we want to do is, instead of using this abstract boundary, we want to use the convergence action that we are given as an auxiliary space, right? It has nothing to do with the space that we are given, the rigid space. But the advantage of this picture is that we get much more than minimality and strong proximality. I mean, a convergence action, you can always take it without loss of generality to be minimal just by restricting to the limit set. But for strong proximality, you see, strong proximality requires that you can take any measure on this set and somehow contract it to a delta measure. And what we get here is that we can do it not with some sequence, but with any sequence. So our strategy in accordance with the how much time I have?
5 minutes.
5 minutes. So our strategy in accordance with Hagerups is the following. Hagerup says, Hagerup says that the following are equivalent. one, for any state phi, one can look at the convex weak star closure of gamma phi, and this contains the canonical trace, and two, there exists S1 up to Sm for every epsilon and any finite set of the group. So there exists a scheme like this, and of course, three, the group is C star simple in the sense that you know, there is a free gamma boundary action. And this implication is basically just a Han-Banach type argument. If you can't separate these gamma 1 up to gamma n, if you can't converge to the identity, there is some state separating their convex closure from the identity. So this is basically just a type of a Han-Banach argument. And what really interests us is trying to do this type of implication, and we follow Hagerup's strategy. Namely, we do the following things. So now we start with some state phi on the cross product. We reduce it to C of x, and this is some measure on this, sorry.
C of z, you mean?
I'm sorry, yeah. Start with some state phi on C, it's a state on the reduced C star algebra of gamma. Okay? Now we look at the other product. We extend it to the cross product with Z, with a different space. And now restrict it to Z, so mu is restricted to C of Z. And we get a measure here. And now we have a measure not on the original space, but on this convergence action. And now we take any gamma n, which is a rigid sequence on X. So we are starting with the sequence which we are interested in, the one that doesn't do anything on the X side, that really converges uniformly to the identity. And we can pass, after passing to a subsequence, we can make sure that it converges the whole space into 2 points in this case. After some acrobatics, you can also contract it to 1 point. I mean, with some games, passing to a subsequence you can have that gamma n lower star of mu converges to delta A. I mean, if it converges on the whole space, just by the Lebesgue dominated convergence, it will also do the same thing to measures. And now you can extend it I mean, you can pass to a further subsequence. pass to a further subsequence such that gamma ni of not just the restriction to CZ, but to phi itself converges to some psi. And now we can use the exact same argument of Hagerup, if you are familiar with it, showing that if we got to a space psi such that psi restricted to C of z is just the delta measure on some point, and the action is free here. Well, the action is not really free, but I'm pushing it under the table. It's just almost free. But assume for a minute that the action is free, then the psi restricted to the fifth-star algebra is actually the canonical trace. And the argument is a beautiful one involving the multiplicative domain. I mean, if this is my point A, and I want to show that this restriction vanishes on some element gamma, using the fact that the action is free, I can find some function that is 1 here, but 0 on the other side. And then if you write something like psi of gamma, of lambda gamma, is equal to f of a, this is the bump function a, times psi of lambda gamma, right? Because this is just 1, which is psi of f times psi of lambda gamma, because psi acts as the delta measure. And now using the fact that this is a function and the measure, a point measure, you know, the multiplicative domain consists of all the functions on this space, you can move this in and out on the other side to get this function translated. So I won't write because I'm writing out of time, but this is equal to psi lambda gamma of psi of f at gamma a, which shows that the whole thing is 0. So this is Hagerup's beautiful argument that, you know, restricting to C of Z, the delta measure really corresponds to restricting to the other side being the canonical trace. And you can work a bit more to show what happens if actually this point is stabilized. But that's basically the point. Okay, thank you.
Do you have any questions for Yair?
So just to understand, at the end, the theorem is with some minimal action of C-star simple groups for C-star cubes.
So the theorem concerns two actions. Okay, I mean the theorem concerns the rigid action. Doesn't have to be minimal. Just any rigid action of, say, a convergence group is reflecting. Okay, is almost reflecting. That's the theorem. Okay? The minimal action is an auxiliary part of the proof. Okay, I'm using the action Z that comes from the fact that I'm having a convergence group. In fact, what we're doing is kind of, you know, propping up Hagerup's argument, and instead of just using it for a general gamma boundary, we're using it for a special gamma boundary, which just gives us the kind of the extra leverage not to contract, you know, not to run this argument with a completely general sequence of elements of the groups that we know nothing about, but to start with a sequence of elements that is uniformly rigid on the given space and start from that. And that's somehow the point.
Thanks.
Yeah.
I have one short question. So when you talked about this construction for rational rotation, where you look at the Fourier coefficients of your potential intermediate algebra, how important it is, at least for this abstract equivalence, that you are working with irrational rotation. What about if you just have a z action on a classical space?
I mean,
On a circle, let's say.
it's very important somehow. It's very important. I mean, we have a hope, though we didn't. I mean, this paper is up for some time, and we said we will do it, and we didn't do anything so far. But we have a good hope of extending this, but to similar situations. Maybe, acting of Zn on its Pontryagin dual, or something, an irrational rotation on a higher dimensional torus, or something of this form. But it really kind of goes deep into Fourier analysis of the... It's very specific somehow.
Okay, if there are no more questions, let's thank Yair. Meet at 10:30. The inclusion is sister simple. The group is sister simple. That is sister simple. That is sister inclusion. It's sister irreducible. Oh, you mean on X itself? Yeah, we don't assume minimality, but you can get a one-to-one correspondence with an ideals.
So, the first was like just pages like this.
So I think that
The operator.
There are no ideals to start with in the reduced sister algebra.
Going back by
Yes, so what is...
in intermediate algebra cannot appear as a
The ideal in the intermediate algebra has to intersect the C of X part.
Opens up to 8p.
That is,
section is not.
intersection could happen. It could be intersection. We're not assuming minimality. Yeah, but the sister simplicity does not mean that the cross product is simple, unless we are minimal.
Yeah, no. So sister simple means that if you take an intermediate algebra,
No,
you take an idea,
no,
this is what I mean.
sister simple doesn't mean for that. For sister
okay.
simplicity means that the group is reduced to sister algebra is simple. This is what
No,
simple.
yeah, I was thinking about something different.
So then we have different definitions.
Probably mine is wrong. But the notion in terminal is the fact that if you take an intermediate algebra,
That we do not know. I mean, that is not true in this
Okay,
case.
yeah.
That is not true in this case. We don't assume minimality. But if you assume minimality, we get it for free. But if you don't assume minimality,
this property is not
but I mean, if you assume minimality, if you don't assume minimality, if you pick an ideal, then the ideal will intersect not clear. That's what we get from
yeah,
it.
exactly. This is why we
Yeah, just run out. I wonder if it connected take a while.
Yeah, you
Run
get
again.
To już coś zrobiłem raz, teraz drugie. No właśnie, a moje zdjęcie chyba było starsze niż Ralfa. Znaczy nie zdjęcie, znaczy zdjęcie obrazka. Franek rysował w przedszkolu. On się już dawno wylogował z systemu. Znaczy on już praktycznie się wylogował, jak już małżonka z nim zamieszkała. Ja bym nie był ten sleep, no idea, znaczy
Here.
Ale zajmiesz to i grać, i ten salę masz sukcesem.
Ile razy tu przyjeżdżam, to zawsze chcę tym samym rozmawiać. Ja zawsze mówię, chociaż potem nie ma sensu, ale znowu dzisiaj
Może masz niedaleko, tam przyjechał na 2 dni, w tygodniu już przyjechał. Czarnowice, zobaczymy. A kiedy na przykład slide napisałem, slide 6. Aha, czyli wiedział w miarę wcześniej. Marca. No zobacz, a musi kiedy nas czeka? Widzisz, droga podwinęła, to się właśnie już wprowadzała tu nas. Zebranych nawet na 30, ale opracowujemy też to jest prawda. Że u nas nie, że u nas zostaje, u nas to zostaje, w sensie ja studentem. To tak, ale później tak trochę się zgadzają ze mną. Systemy edukacyjne, no, albo tacy słabi, albo z jakimś defektem, no jakiś defekt ogólnie rozumiany. Z różnych przyczyn. Nie możemy się zgadzać. Naprawdę dobrze zainteresowani matematyką.
najbliższy and you can kind of see the price. You might scale away the price. Why should I see the price? Why something
Yes.
Anna, you're going to use black? I have one stick left, so we share. Some starvation rations.
Nawet są odbijane rodziny, ale są stawki, jak niektórzy nie radzę bardziej tak nie napaść. Ale jak masz zamek, to widzę, to sugeruje oblężenie raczej. Ja drabinie nie kupiłeś się? Raczej tak. cały ciąg